All right, let's dive right in. Today, we're talking about the absolute heart of Java programming. I mean, the real fundamental logic, the stuff that everything else is built on top of.
Seriously, think about it for a second. How do you go from a completely blank screen to a working application? It's not just about typing weird symbols, right? It's a creative process. It's like being an architect and a builder all at once.
Well, to start building anything, you need a good toolkit. And that's exactly what core Java is. Think of it as your starter set of tools, your essential materials. Basically, the Java Standard Edition. This is the stuff every single developer has to get really, really good at before they can even think about building something big and complex.
I mean, just like building a skyscraper, you can't just start throwing up walls. You need a solid, logical foundation. So let's start there, understanding what holds this whole thing up. All right, so what are our raw materials? In a building project, we'd be talking about bricks, mortar, maybe some steel beams. Well, in programming, our most basic raw materials are variables and data types. This is the stuff we actually build with.
So what on earth is a variable? It's just a container. That's it. It's like a little labeled box where you can stash some information you're going to need later. It's the most basic, fundamental way we hang on to data in our code.
And, not all boxes are the same. You wouldn't try to carry water in a cardboard box, would you? It's the same in code. We have different types of containers for different kinds of stuff. We call these data types. So you've got your integer for whole numbers like 10 or 42, and you've got a Boolean for a simple yes or no, a true or a false. Different tools for different jobs.
Okay, so we've got our materials, but a pile of bricks doesn't just turn into a house, right? You need tools and you need a set of instructions. And that's where operators and control flow come into play. This is the part that lets our program actually do things, make decisions, repeat tasks, you name it.
So what is control flow? Think of it as the instruction manual for your code. It's what dictates the flow. It tells the program which step to take next and when. Without control flow, our code would just be a dumb list of commands executed one after another with no intelligence at all. And the most basic kind of decision-making you can have is the if-else statement. It's literally just a fork in the road. The code asks a question, is this condition true? So if it's raining outside, then do action A, grab an umbrella. Else, if it's not raining, do action B, grab some sunglasses. It's so simple, but it's the foundation of all logic and programming. Incredibly powerful. But what about stuff you have to do again and again? I mean, imagine you're programming a robot on an assembly line. Are you going to write out the instruction, put on a wheel 100 times? No way! That would be insane. That's where loops come in. You just write the instruction once and say, hey, keep doing this until you're done. It's the power of repetition, and it saves us a ton of work. All right, so we've covered the bricks and the tools. Now, let's zoom out and look at the architect's blueprint. This is where we get into something called object-oriented programming, or OOP for short. This is the philosophy, the design plan for building really big, well-organized, and scalable applications. And the whole power of Java's OOP approach really rests on these four main ideas, these four pillars. Now, I know the names sound a little academic. Encapsulation, inheritance, but don't worry about that. Each one is just a smart principle for writing better, more flexible code. Let's quickly break them down. First up, encapsulation. Okay, the best analogy for this is a car engine. When you drive a car, you have a steering wheel and pedals. That's your simple interface. You don't need to know how the pistons are firing. All that complexity is encapsulated. It's bundled up and hidden away inside the engine block. That's what encapsulation does in code. It bundles data and the methods that work on that data into a neat, protected package. Next up, inheritance. This one is all about not reinventing the wheel, literally. Let's say you've already designed a car. It has wheels, an engine, seats. Now you want to design a sports car. Instead of starting from scratch, you can say the sports car inherits everything from the base car, and then you just add the cool new stuff, like a spoiler or a turbo. It's all about code reuse. Polymorphism. Yeah, another big word, but the concept is actually pretty straightforward. It literally means many forms. Think about a start engine button. On a gas car, it starts a gasoline engine. On an electric car, it starts an electric motor. The action, start engine, is the same, but what actually happens is different depending on the object. That's polymorphism. It makes your code super flexible. And our last pillar, abstraction.
This is all about hiding complexity. When you get in your car and turn the key, you just expect it to start. You don't need a PhD in mechanical engineering to do it. All the messy, complex details of how the engine works are abstracted away from you. You're just given a simple interface, the key. Abstraction in code does the exact same thing.
So this brings us to a really, really important distinction, the difference between a class and an object. A class is the blueprint. It's the design on paper for a house. An object is the actual physical house you build from that blueprint. You can have one blueprint, one class, but you can build a whole neighborhood of actual houses, hundreds of objects, from that one single plan. That's a key concept.
Okay, we've got our materials, we've got our tools, and we've seen the architectural blueprint. So for our last section, let's put it all together. Let's see how these pieces of logic actually click into place in a real, albeit tiny, piece of code.
Okay, take a look at this. Super simple. First line, we create our container, a variable. It's an integer, we've named it number, and we put the value 10 inside it. Easy enough. Then we hit our if-else statement, our decision point. Now, what's this funky little percent sign? That's the remainder operator. All we're asking is, if you divide the number by 2, is there a remainder of 0? Well, 10 divided by 2 is 5 with no remainder, so the condition is true. And because it's true, the program prints out the number is even. See how that works? We used a variable, an operator, and control flow to solve a problem. That's programming right there.
And honestly, that's the whole point. Getting a handle on these core concepts, it's not just about acing a coding interview. It's about really learning the language of logic. When you understand this stuff, you can start writing code that isn't just a jumbled mess that happens to work. You can write code that's clean, efficient, and that you or someone else can actually understand 6 months from now. So there you have it. You've got the toolkit, you've got the raw materials, and you've got the blueprint for thinking logically in Java. The only real question left is, what are you gonna build?